Hello everyone, I'm Sarika 17E092 and I'm going to take a seminar on the topic Challenges in HVDC. First, let us see the advantages of HVDC over AC transmission. High voltage direct current transmissions are gaining relevance in long distance and renewable energy integration projects over the conventional alternating current transmissions. HVDC technology offers several advantages over the traditional AC technology, making it a promising and cheaper solution for future expansions of the grid or for new interconnections. This is due to several advantages as improved flexibility and independent active and reactive power controllability. Advantages of HVDC: lower power losses and cost in long distance power links than the AC transmission. It requires a lesser number of electrical conductors, thus also reducing the cost. Lower weight are needed to transmit the same amount of power which is transmitted via AC transmission. Capability of transmitting power over long distances with underground or undersea cables. And it is also capable of interconnecting asynchronous grids. Challenges in HVDC transmission. However, HVDC grids are similar to high voltage alternating current grids are not failure proof. Even though they have many advantages over the it's not completely perfect. It also has some failures. Fault between conductors and ground can happen. During fault conditions in an HVDC grid, two critical situations take place. The voltage drops sharply and the current increases rapidly to very high values, which is critical in grids with voltage source converters, the modern HVDC technology. Its power electronic devices can withstand only twice its rated current and not the high fault induced currents. If the fault is not cleared very fast, the VSC converter needs protection. If this is the case, the entire HVDC grid can be lost with the corresponding large blackout. Protection requirements needed for these challenges. Fault conditions are dangerous not only for the system equipment but also for people. Therefore, they should be isolated and cleared as fast as possible. Hence, HVDC protection systems have to ensure safety and minimize fault impact and component stress. Protection systems must operate satisfying some performance requirements. The requirements are accuracy, speed, sensitivity, selectivity, recoverability. In accuracy, the protection system only operates when the fault condition is located inside its protection zone. Speed. In speed, fast operation in order to avoid damage on equipment and to minimize the fault impact. This time covers the detection and identification times of the protection algorithm and the operation time of the circuit breakers. In sensitivity, all relevant fault conditions must be detected. In selectivity, internal and external fault conditions must be properly differentiated and the isolated zone should be as small as possible. In recoverability, the system must reach a stable state after fault clearance. These are the protection requirements. These components are mainly in protection systems. There are three main components. Those are measurement devices, protection algorithms, circuit breakers. Measurement devices are in charge of adapting the signals needed by the relays to operate properly. Protection algorithms use these measurements in order to discriminate between normal and fault conditions. Circuit breakers isolate the faulty part of the system, interrupting the current. The adopted fault clearing strategy determines the impact of a fault condition on the system. First, let us see about measurement devices. Measurement devices adopt the voltage and current signals so protection relays can properly use them. There are two types of measurement devices according to the measured signal: current measurement devices and voltage measurement devices. In voltage measurement devices, the capacitive compensated resistive voltage divider is the most used primary sensor in DC applications. It consists of a resistor and a capacitor in parallel connection. Several RC groups connected in series allow the reduction of the primary voltage amplitude. This way, a high bandwidth of a few megahertz can be achieved, which will be limited by resonance effects due to stray inductances in the capacitive part. In current measurement devices, there are different types of measurement devices which adopt the current signal. These are mainly zero flux devices, fiber optic current sensors, and hybrid electro optical transducers. Let us see about them one by one. First, zero flux devices. A DC current transformer is a zero flux device which consists of two magnetic cores and three windings. Two of these windings measure the flux generated by the direct current, and the remaining winding compensates the flux. A fiber optic cable wrapped around the conductor constitutes the fiber optic current sensor, which is based on the Faraday effect. The speed difference between two polarized light waves is equivalent to the current measurement. The combination of a Rogowski coil, a shunt, and optical transmissions is a hybrid electro-optical transducer, which consists of an electrical sensor and optical transmissions to isolate the primary and secondary sides of the device. Now let us see about protection algorithms. Fault conditions must be detected and located in a range of time shorter than 10 milliseconds in HVDC systems, as it has been mentioned previously. Protection algorithms are in charge of locating and detecting fault conditions. They can be classified into local measurement based or communication based algorithms. First, local measurement based algorithms are very fast since they only use locally available measurements. However, these algorithms lack selectivity and they are sensitive to misdetection of external faults. Communication based algorithms are based on exchanging data information between both ends of the protection zone. Then they are inherently selective, but they depend on the communication channel medium and the time delay imposed by it. Now let us see about circuit breakers. HVDC circuit breakers must offer short operating time and high current interruption capability. In addition, they must produce a current zero in order to interrupt the current since it does not cross a zero naturally as in AC systems. The most common types of HVDC circuit breakers are mechanical, solid state, and hybrid circuit breakers. First, mechanical circuit breakers. This type of circuit breaker presents a mechanical breaker in the main conduction branch, a LC resonant circuit in the commutation branch, and the energy absorption branch. Solid state circuit breakers. They consist of a main conduction branch, an energy absorption branch, and no commutation branch. The current is directly commutated from the main branch to the absorption branch. Hybrid circuit breakers. They combine the advantages of the solid state and mechanical circuit breakers, that is, fast operation in the range 2 to 5 milliseconds and lower on-state losses. They consist of a small number of power electronic devices and a mechanical switch in the main conduction branch. Fault clearing strategies. This consists mainly of three types of strategies. They are non-selective strategy, full selective strategy, partially selective strategy. First, non-selective strategy. The entire system is shut down when a fault condition is detected. AC circuit breakers are usually in charge of doing this. Then the faulty part is isolated using DC switches located at both ends of each zone. Now, full selective strategy. The system is divided into different protection zones in order to disconnect only the faulty zone. HVDC circuit breakers are located at both ends of every protection zone. Partially selective strategy. This strategy combines the previous ones, that is, both the non-selective strategy and full selective strategy. The system is partitioned into several protection zones interconnected by DC links. HVDC circuit breakers or DC to DC converters are placed on the interconnecting links in order to disconnect the faulty zone from the healthy zones after the fault detection. And it is now time to conclude. The importance of the speed requirement must be highlighted since it is critical in HVDC systems. Hence, local measurement based algorithms are mostly used since they present fast operation. However, they need limiting indictors to improve its selectivity. Thank you.